Furen International School presents A-Level Physics, Cambridge International Style. We're still in Topic 1, Physical Quantities and Units, and well done, you've made it to Lesson 2. So we're back. I'm Patrick Van Twest, and I'll be guiding you through Lesson 2 of this topic. So last week we looked at physical quantities and SI, or System International units, and today we'll be looking at errors and uncertainties and scalars and vectors. So are you ready to get started? Let's start. Some key words for this lesson. There's many of them, so here they are. Error, uncertain or uncertainty, vernier calipers, micrometer screw gauge, accurate or accuracy, precise or precision, systematic error, random error, fractional uncertainty, scalar, vector, resultant, component. So please be familiar with all these words, understanding what they mean. So errors and uncertainties, can you believe that scientists actually make errors and they're not very completely 100% certain of everything they find? Yes, even the best scientists have errors and uncertainties in their work, but a good scientist will know the source of their errors and they'll have a good feel for how certain and how uncertain they are with their measurements. So what is an uncertainty? Well, it's a range of values within which the measurement is likely to lie. So for an example, if I were to say 46.3 plus or minus 0.5 grams, that means the 0.5 plus or minus means I'm uncertain about that 0.5 above or 0.5 below. So what are the sources of uncertainty? Well, they say, a poor tradesman blames his tools. And for scientists, it's kind of true. We're always limited by the instruments we use. So instruments in themselves have only a certain amount which we can measure the smallest division. So there's a limit to how precise we can be with our instruments. So for example, a meter rule that you've probably used a lot, its smallest unit is a millimeter. So you can't get any more precise than 1 millimeter. So let's have a look at the smallest unit for these measuring instruments. So 0.1 or 1/10 of a centimeter for a meter rule. Now if you want to get more precise, you can use vernier calipers, which you'll probably use in the lab and learn how to use. So with vernier calipers, we can get down to 1/100th of a centimeter. And then if you want to get even more precise, the micrometer screw gauge allows you to get 1,000th of a centimeter. But still, there is a limit to how small we can go with our smallest division. So what might affect the accuracy and the precision of measurements for scientists? Well, accuracy is the degree to which a measurement approaches the true or real value, the actual value. So what do you think might influence the accuracy of a measurement? Well, you might think of things like this. It could be the nature of the experiment, just how the experiment is done. It might be, like we said before, the instruments we use to measure. It could also have a lot to do with the skill of the experimenter and their experience, and also the techniques used. So when you do your practical part of the course, you'll try to get better at using accurate techniques and developing good skills for measuring and trying to eliminate any sources of inaccuracy. Now, precision is a different animal altogether. Precision is slightly different. It's that part of the accuracy which the experimenter can control. So let's look at some differences between accuracy and precision. So here we've got a bullseye, or like a darts board, and the center of that board represents the true value. So can you see 4 different experiments here with a range of measurements? Can you see the difference between them? So on the top left here, we'll see that these little points here, they're not accurate because they're missing the mark. Can you see they're all scattered off the mark, and they're not precise either. They're sort of spread around a big range. So you'd say those are not accurate results, they're not precise either. Whereas if you go down to this one here, you'll see these are accurate results because they're zoomed in, they're centered on the true value, they're averaged out to the true value, but they're not very precise, they're spread out again. If we go up here, these ones are very precise, so all the results are very close together, the results are close together, but they're not accurate. They're still far from the true value. whereas this one, this would be the one I'd want. I'd want accurate and I'd want precise. So all the measurements are close to the true value and they're also very close together. That's what we're aiming for as scientists. Another way we can represent that is with this sort of chart. Okay, so you'll see here, this reference value or the true value of a measurement might be here, and then our results might be, spread out like this. So the accuracy would be how far our average is away from the true value, and our precision sort of measures the spread of those results. What's the range of our results that we took? Okay, so here's an actual exam question that you could try. So I encourage you maybe just pause the video here, try this, and see if you can work out which set of these results, 4 results, A, B, C, and D, which ones could be described as precise but not accurate. Okay, I hope you paused and tried that. How did you go? Well, this is how I would do this question. It first asks about what is precise. So precise means the range of values is small. So if you can see on this question, both A and D, if you look at the sets of results, all those numbers are pretty close together. And same with D, these numbers are close together. So both A and D are precise, but which one is not accurate? Well, accurate, remember, means it's close to the true value. So we know from experience with physics that the free fall acceleration near the Earth is 9.8 meters per second squared. You'll get to know that very well in your course, trust me. So we can see that the A is very close to that. So we would say A is accurate, but look at the results for D. Even though they're precise, they're still a fair bit off this 9.8. They're not close to 9.8. So that one is not accurate, but it is precise. That is the answer we're looking for in this question. Okay, so where do errors come from? If a good scientist will know, the source of their errors and then try to reduce them. So there's 2 main types of errors that we talk about in physics. They're systematic errors and random errors. What do those terms mean? Well, systematic errors have definite causes and are reproducible, whereas random errors have non-specific causes and are not reproducible. They're random. That's why they call them random errors. A systematic error has a constant error due to its cause. So all the readings will have a constant error. So you can see on this chart here, all the measurements are slightly above the true value. It's a constant error. But look at the random errors. The readings are scattered randomly around the true value. So if you look at all these measurements, they're both above and below the true value and they're scattered around randomly. A systematic error leads to poor accuracy, as you can see, whereas a random error might be accurate, but it leads to poor precision because the results are scattered. Systematic errors cannot be eliminated by averaging, but random errors can. So that's a very handy thing. If you take an average of your readings, you can eliminate random errors. An example of a systematic error might be just a problem with your measuring instrument, a constant error with that instrument. And example of a random error might just be the randomness of the observer or of the conditions. And sometimes all things we do have a touch of randomness in them. Right, here's some particular examples. So you might be familiar with this device. It's a spring balance to measure. What does it measure? Yes, it measures force. So this particular spring balance you can see has what we call a zero error. What that means is even though there's no load or there's zero force, it's still reading 1 Newton. If you can see that, it's reading 1 Newton. So the spring balance does not read 0 even when there's zero load. So we call this a systematic error. All the readings are going to read 1 Newton bigger than the true value. Another type of error we have to be particularly aware of is something called parallax error. Parallax. So if you look at this picture here, observers 1 and 3 are looking at the ruler at an angle, whereas observer 2 is looking directly onto the ruler. So you'll see that observers 1 and 3 will have a systematic error in their measurements. Why is that? Well, observer 1 you can see is reading a bit bigger than the true value because of his angle, and observer 3, because of her angle, is reading a bit smaller than the true value. Here's some other examples. If you ever try to time a moving object, like a pendulum, there goes that pendulum. Can you time it? Just say you're timing the period, for example. Timing these is very difficult because the object is moving. Okay, so there's going to be random errors when we try with a handheld stopwatch to measure this thing because we just don't know exactly with our eye exactly where it is at any point in time. And there'll be a random error when we take timings, and multiple readings will be scattered around the true value. Okay, what if you were to measure something like temperature? You might think, well, that's a fairly standard thing to do to measure temperature, but you should realize that maybe the object you're measuring, the temperature, might be fluctuating due to changes in the environment. So again, that would be a random sort of error. What that would mean is the readings of temperature would be scattered randomly around the true value. So that's another sort of random error, is just fluctuations in the environment or in the object itself. So here's an example question. Again, I just encourage you to pause the video, try it out, read through all the options and see it's multiple choice. Just have a guess, or better than a guess, try to work out what's the best answer for this question. Okay, did you try it? So here's a speedometer measuring speed in a car, and it contains a pointer, and the pointer, it says, very important here, it says it's situated several millimeters from the calibrated scale. So what that means is I've got a scale that I'm looking at and my pointer is moving here measuring speed, and then I'm looking at the pointer and the scale. So which one of these would cause a random error? Well, I think it would be this one B, because you see if I move my head slightly, I'm going to be moving my head and getting slightly different readings from the pointer to the scale. Okay, now very important topic here is uncertainties. What do we do with them in our measurements or in our experiments? So very often you'll have more than one quantity that you're measuring, and you'll want to do some calculations with those quantities, and you'll need to know what to do with the uncertainties. So when quantities are added, subtracted, multiplied, or divided, basically any operation you can do with a quantity, we've got some rules that you can use to know what to do with the uncertainties. So firstly, let's look at what happens if we add or subtract quantities. That's all these ones in white here. What we need to do is we do something with the actual uncertainty. So can you see this here? The actual uncertainty is what we've labeled here as change in Q. Change in Q, that's the actual uncertainty. And when we add or subtract, you can see either way, if I'm adding and even if I'm subtracting, notice that? Even if I'm taking away quantities, the uncertainties add up. They add up, the actual uncertainties. Now, when we multiply or divide things, so when we multiply or divide quantities, now we're doing something different. Okay, so now instead of actual uncertainties, I'm dealing with something we call fractional. Sounds the same, actual and fractional. But fractional uncertainties, can you see what the difference is? It's the uncertainty divided by the actual quantity. Divided by the actual quantity. And what I do there is I add up the fractional, or sometimes they call percentage uncertainties. Okay? So I'm adding the fractions. And even if I divide, can you see it's the same? I'm still adding fractional uncertainties. So let's practice these rules because they're quite important. Okay, so here's an example. We've got two currents entering a junction, current I1, I2, and they add up to I, the total current leaving the junction. So obviously I1 plus I2 equals current I. And in an experiment, we've measured the total current I and we've measured the current I1. And we've got some values and we've got some uncertainties with our measurements. And now the question is asking, what is the value of I2 and what's its uncertainty? So the value of I2 is quite simply just the difference in the quantities. So just taking away the quantities, we end up with 1.5 amps. That's quite basic, but what happens to the uncertainty? Now, can you see uncertainty? We're subtracting quantities, but careful, we're adding the uncertainty, the actual uncertainty. So can you see the uncertainty in the total current was 0.1, the uncertainty in the I1 is 0.2, and these are added. Okay, so we're adding. So our final measurement would be 1.5 plus or minus the 0.3 uncertainty. Now, okay, just to complicate matters a bit more, we don't always add or subtract with our formulas. Physics, sometimes we get quite involved formulas. We might have a constant out the front, we might have, a power, and then we might have a different power, and we could even be dividing powers and things. Okay, so what happens in these cases? Well, you'll notice that we're dealing with fractional uncertainties. Okay, why is that? Well, whenever we have a power, that just means x multiplied by x multiplied by x, m times, and y times y, n times, or dividing. So we're multiplying or dividing always. So we're dealing with fractional uncertainties. There's our friend again, fractional uncertainty. So when we have that, we take the fractional uncertainty in x and multiply by itself, multiply it by m, and we multiply the fractional uncertainty in y times n. Notice that any constants, don't have any effect on the uncertainties. Okay, so best thing to do now, try an example. So again, I encourage you, pause the video, try this one out. There's quite a lot of numbers there, but a really good question for you to try. Try to cover over this answer, the answer's there, but try to do it without the answer and then come back and see if you agree. So I hope you've done that. So here's the answer. So you need to look at this problem. We've got an equation now with a constant for another constant pi squared, and then length is a measurement and period is a measurement. So we're actually just measuring two things and putting it into a formula. So in this experiment, the length was measured with a certain uncertainty. The period was also measured with a certain uncertainty, and now we want to end up with the value of g. So to get the value of g, we just put in the numbers. So we put in the actual measurement there, can you see? Length, and then we put in the actual period, and we square it, and we do the formula. And if do some maths, you'll get this as your actual value of g. But there's an uncertainty that comes with it. Why is there an uncertainty? Well, there's an uncertainty in the length, and there's also an uncertainty in the period. What do we do with uncertainties? Well, because we're multiplying and dividing everything, we have to deal with fractional uncertainties. Okay, so this should actually say here, not uncertainty, but it should say, I'll just put FR, fractional uncertainty is the fractional uncertainty in L plus twice the fractional uncertainty in the period. Why is it twice here? Why is it twice? Can you see? Did you get it? Yes, because the period is squared. Okay, so we need to double the fractional uncertainty in t, or it's just t, the fractional uncertainty in t added to itself. So when we put in the numbers, so you see 0.03 divided by the actual quantity for length, and then the same with period, the uncertainty is 0.2 divided by the actual measurement 1.7. Now you can see here that the fractional uncertainty in the length is very small. That's, about 0.4%, which is a very small uncertainty, but the fractional uncertainty in the period, look at that. That's about 12%. So that's quite a big uncertainty. And then, because I'm squaring the period, I'm doubling that uncertainty. So can you see my final uncertainty is up around 24%. So that's quite a big uncertainty. So if I want the actual uncertainty, I multiply the fraction times by the actual value there, the 9.79. That gets me the actual uncertainty. So my final answer would be the 9.8 meters per second squared plus or minus this 2.3, the uncertainty. Also, just notice how we've taken two significant figures in our answer. Why is that? Well, look at our measurements. We're restricted here by two significant figures in our time, our period. So we should only have two significant figures in our answer. Okay, moving on to scalars and vectors. Scalars and vectors. These two different types of quantity. A scalar quantity has magnitude or size only. So things like distance, things like mass or time or speed, or maybe this bottle again, the length of this bottle, the mass of this bottle, they're scalar quantities. They just have a size or a number. But a vector quantity has two things. That's two things, both magnitude and direction. Now, you might have seen this comic figure before. This character is called Vector. Okay, and if you saw the movie, he called himself Vector because he said he has magnitude and he had direction. He had a purpose. So that's a good way to remember actually what a vector does. A vector, or what a vector is, a vector has both magnitude and direction. So things like displacement, weight, which is a force, velocity, a force again, they're all vector quantities. So throughout this course, you might often be asked, with every quantity you meet, you might be asked, is it a scalar or is it a vector? The key is, does it have direction? So if we have a vector quantity, we can represent it. Represent, with an arrow and a line. So in this case, the big yellow arrow represents the direction, and the length of that arrow represents the magnitude. So here's some example. Small purple arrow might mean 1 meter east. So what would bigger purple arrow mean? That's right, it's a bigger vector, 2 meters, but same direction, east. Can you see? Right, your turn. What's this one? What might this be? Well, it's got to be east, and it's got to be bigger, so it's 5 meters east. Right, try this one. What do you think of that one? Yes, it's the same size, 5 meters, but it's reverse direction, so that vector is 5 meters west. You get the idea? Vectors. We love them, vectors. So what do we do if we add and subtract or different things with scalars and vectors? So with scalars, it's really quite simple, and it's probably something you've been doing since you're very young. You've been adding numbers, adding quantities, and they're scalars. They just have size, so they simply just add. But when you add vectors, you have to be a bit careful because those vectors have directions. Okay, so if the direction is not the same for each vector, then you can't just add them like you do scalars. You have to do something a bit different. You have to learn how to add vectors. Okay, so there's two different examples I'll give you here. One using the triangle rule to get an answer, one using the parallelogram rule, but both have the same process. So just watch carefully how I do this. If I want to add vector A and vector B, you see they're in different directions, and in this case they're at 90 degrees to each other. So I start with one of the vectors. I'm just going to start with A, but I could start with B, and I'm just going to draw it again. Okay, so I take the same size, same direction, and I just move it over here, and then I take the second vector that I want to add and I slide it in position, so same size, same direction, and can you see what I've done? I've done tail to head. So I've gone tail to head, and then with B I've gone tail to head. And if I wanted to work out that size, the size of that line, I could just use my friend Pythagoras, right angle triangle. So this is where we actually use some math, some geometry, to work out the size of A plus B. And if I wanted to work out the angle, where we use our friend's trigonometry, I could work out the angle that this vector is at from trigonometry. Okay, you try this one. What if B and C now are not at 90 degrees? How could we do this one? Okay, where would you start? Well, same sort of thing. We could start with either vector. So if I start with C, I just draw the same vector starting here, and then I slide B so that, again, I've gone tail to head, and then I just go from start to finish of what I've drawn. I join start to finish, and there is my resultant, or what we call the total resultant, C plus B. And if you wanted to work out that magnitude, again, you can just use some geometry. Parallelogram rule can get you that size and the direction. What about subtracting vectors? Okay, is that a lot more difficult? Well, no, not really, because if we want to subtract two things like Q and Q minus P, I just have to remember that Q minus P is the same as Q plus negative P. So instead of subtracting, I'm just adding Q plus negative P. So if this is P, what does negative P look like? Negative P, what is it? Well, it's a vector. So negative P would be just the same size with the opposite direction. Can you see? And now if I want to add P to negative Q, I just do the same thing. I start with my Q, and then I add here my negative P, tail to head, start to finish, and there's my resultant, Q minus P. And the same thing, triangle rule can give us the size and direction. Same thing again with parallelogram rule. If I'm subtracting two vectors that are not at 90 degrees, again, I just replace, instead of B, I draw negative B. So negative B would be in that direction, opposite to B. and then I just do tail to head again. So I start with A, vector A here, and then I add negative B. So there's negative B, start to finish, there's my resultant, A minus B. I really recommend you practice a lot of these by actually drawing them and doing lots of practice just to get used to adding vectors. It's not something we naturally do from when we're small, so it's good to practice as much as you can. So here's an exam question. Try this one. Okay, so maybe pause again. Try this question. We've got P and Q. Which vector, A, B, C, or D, would be best representing P subtract Q? Did you try? Did you try? I hope you tried. So here's what I would do. I would do minus Q first. I'd actually draw it on my paper. I'd draw negative Q, and then I'd slide it across. So I'd have P, starting from this point, P subtract Q, or P plus minus Q, starting here, finishing here, join them up. So the green line would be P minus Q, which looks like D. So I would circle answer D. Finally today, we're going to look at vector components. So it's very handy often is to split up a single vector into two vectors, especially if those two vectors are at right angles. Okay, we often call them components. And we call the process resolving a vector into two components. So just an example here, I've got vector A here, length with the direction, and it's at an angle theta to the horizontal. I can write that same vector as AX plus AY. So if you were to do vector addition, if you were to move this vector AY over here, and go tail to head, then start to finish would give you the same vector as A. And if you wanted to work out those components, again, just using a bit of trigonometry, AX is A times cos theta, AY is A times sine theta, and if you want to work out the size of A, you just use Pythagoras' theorem there. Okay, and a bit of trigonometry again. So this is a very common process in A-level physics, is dividing a single vector into two vectors at 90 degrees to each other. It's called resolving into components. Well, that's it for lesson 2, and that's it for the first topic of your course. Just a summary of today's lesson to refresh your memory. Scientists make errors, yes, it's true, and they're not always 100% certain about everything they measure. So we looked at the difference between accuracy and precision, and we also looked at the difference between systematic and random errors. Also, we looked at what you do with uncertainties. Adding uncertainties always. So uncertainties always add. You know, if you have one uncertainty, you have another one. They never take away. They always just add upon each other. And that's if you have more than one quantity. Sometimes you'll have to add fractional uncertainties, sometimes the actual uncertainties. And then we had a quick look at scalars and vectors, the differences between them. And we also looked at how you would add and subtract scalars or vectors. So we hope you enjoyed today. Oh, we also looked at components of vectors, components. Hope you enjoyed today. Here's the keywords again. So just running through these words. See if, as I say them, see if you can remember what they mean. Error, uncertain or uncertainty, vernier calipers, micrometer screw gauge. Remember those instruments. Accurate or accuracy. Do you remember what that means? Precise or precision, systematic error, random error, fractional uncertainty, scalar, vector, resultant, and component. So that's it for lesson 2. Until next time, we hope that you will rise above the ordinary.
Welcome to Furen International School, Singapore. We have international staff with global work experience and students with the highest academic achievements. Our modern city campus is equipped with state-of-the-art learning facilities and a practical science laboratory. And our focus is on student development to mold them into a global citizen. Singapore, the vibrant, first world economy of Southeast Asia, is the perfect home for an advanced learning center. We are located just off the city's upscale Orchard Road. We lead the way in preparing entry into world-class universities. FI students with strong grades enter universities from all over the world. Many will enter a global top 100 university. Our brightest will enter Oxford and Cambridge and other G5 institutions. Not forgetting Singapore's best universities. Our students have scores top in the world grades in maths and other subjects. They are encouraged to debate in the Model United Nations and are groomed to be leaders of tomorrow.
如果一定说辅仁对孩子们做了一些特别的地方的话，那就是老师们对教学的认真和对孩子们的关爱。有孩子说，我很难想象一个老师，我很晚了，有时候11点钟发信息给老师，老师也会及时的回复我的信息，这是他们在辅仁学习当中感觉印象深刻的一点。所以呢，如果说辅仁在某一方面能做得相对成功的话，这是师生共同努力的结果。所以在此我非常感谢孩子们为自己的未来肯拼搏，也感谢家长给予我们的信任，也感谢代理呢给予我们的支持，使得我们这样普普通通的学校，因为这些有理想的孩子的云集，有努力的一群对教育有热忱的老师环绕在孩子们身边，使得孩子们的升学有这样还算令人满意的结果。所以在此我表示深深的感谢，谢谢大家。
Our students score very high marks in the core sciences and maths. Many go on to careers in science, computing, and engineering with a new medical pathway now on offer.
Our students are very fortunate to have the Cambridge International Examination as their pathway to university success. Our students have wonderful, dedicated teachers who lead them and guide them and help them at every step of the way in their journey. Our school is a centre of innovation. It is a progressive environment where we give all of our students every opportunity to succeed.
Middle school students also engage in the arts, robotics, and swimming, and a range of activities to stimulate their minds and keep bodies fit. Student welfare is important to us, teachers and staff counsel students and understand their needs. Our school is also a centre for IELTS study and SATs examinations. High school students are encouraged to focus on their academics in 18, 24 or 36-month programs. Students at FIS make good friends and will learn to bond at our hosted facility, called JJ's. Learning independence is a positive step in a Furen student's life. Singapore is a safe and convenient destination for students from everywhere, whose desire is to make their mark on the world. Join us to take the next step in an exciting and wonderful future. Start your pathway to a world-class university at a world-class preparatory school. We look forward to seeing you soon.